All right, so here we have another technique for analyzing circuits, DC circuits, and of course this works for AC as well, but we're doing DC for now. This is called source transformations. So this is another technique where you're going to take the circuit you're interested in, mess with it so it looks like something else, which is easier, and then it happens that if you mess with it in the correct way, the answer you get from the simplified thing is the same as with what you started. So if you have something very complicated, if you could find a way to make it simple, but still give you the same answer, then why work on a complicated thing? Work on the easy thing. So in this case, what we're going to do is we're going to take a circuit which may have voltage sources or current sources or both, and convert one type of source into a different type of source. And what I mean by that is something like this. Say we have a voltage source with a resistor in series, okay, and it goes off to some other part of the resistor, the circuit. So we'll call these terminals A and B, but there may be other parts of the circuit connected over there. I'll call this the resistor, and this will be my voltage source. It turns out that there's a way to manipulate this to create a current source and a resistor connected to these terminals that would behave the same way as the voltage source with the resistor. The difference is, in the voltage source with the resistor is connected in series with the voltage source. However, if I convert this to the current source, then you're going to have some current source, and it's connected to the resistor, but it's connected in parallel. And that's connected to my terminals over here, A and B. This is R, this is some current source. Now, here's something important to understand. These resistors, the R on the left side and the R on the right side, are the same resistor. So if you remember when we did other techniques, let's say delta Y transformation, you were converting the three resistors that were in the Y connection to three different resistors in a delta connection that happened to give rise to the same answer. But there were different resistors. You had to calculate those new numbers. Here, that's not true. If you have a voltage source in series with a resistor, I can convert it mathematically into acting like a current source in parallel with the same resistor. So the only calculation that's going to be involved here is if I happen to know what R is, and I know the voltage source I started with, then all I have to do is calculate what must be this current source that allows this to be true. Okay, the R will not change here. And the good news is, we already know how to do this calculation. It's just Ohm's law. So it just says that the current source you would need for this to be true is the voltage source from the original divided by the resistor. Okay, it's just V equals IR, or I is V over R. So very nice, very easy little thing, but let's see it in action. Let's get an idea of how this might work. Let's say we have this particular circuit. So we have a current source, a resistor, voltage source. I'll let this be 9, I'll let this be 5, I'll let this be 4, 3, and 10. And the question is, find I naught, the current running between resistors 4 and 3. Okay? That's the objective. I want to know what's the current running through resistors 4 and 3. So we have different techniques to try this. Maybe nodal analysis will work. Maybe loop analysis will work. I could try different things. But let's try it using this method and see where it leads. So the first thing you're going to notice is there's two different sources here. I've got a current source in parallel with the resistor of 5, but I also have a voltage source, 10, in series with 3. So which transformation do I want to do? Well, that's up to you, but what you're going to find as you get more and more comfortable with this is look at the circuit and see which step would actually make things easier for you. If I were to try to take this part of the circuit, the voltage source in series with the resistor of 3, and I convert it, then what's going to happen is it's going to turn into a current source, and that resistor of 3 is now going to be in parallel with that current source. So you're going to get something like this resistor will be here, and you'll have a current source like this. Okay, so you won't have this stuff, you'll have the gray part there. But notice, okay, I've got two current sources, no big deal, but now I've got this kind of squarish looking set of resistors here, where are they in series, are they parallel? That's kind of not very clear. All right, well, what would happen if I tried the other way? If I took this set over here, it's a current source in parallel with a resistor. If I were to convert that, what would happen is, well, the current source becomes a voltage source, and its resistor will be in series with it. And so you'll have something like this, where now this isn't here anymore, and this isn't here anymore. Well, notice there you'll have this voltage source here on the left, and then you have resistor, resistor, resistor in series, and then another voltage source on the right. So all the resistors will be in series. Well, that's very nice, because of course, one thing we can do, given things like superposition, if I have two voltage sources in series with each other, well, I could just add the voltage sources together to give me a total voltage, as if it's just one source. And then I've got all those resistors in series. Well, whatever the current is in one of the resistors, that's the current in all of them. We found that in the first week of circuits as well. So that's actually an easier problem to solve. So that's the way we're going to go. So let me go ahead and get rid of all this gray, and we'll see it in action. Again, don't worry if when you look at it you say, well, I don't know which one to do yet. That's what practice is all about. I'm going to show you why this way is easy. And then as you do more and more practice problems, you'll become more and more comfortable with this. So I'm going to take this part of the circuit right here, and I'm going to say what it is a current source in parallel with a resistor, and that's connected to the rest of my circuit, right? That's like here and here. This resistor is a 5, this is a 9, and all the stuff on the right I don't care about for now. And what I want to do is convert this into a voltage source in series with a resistor. Now, here's something I didn't mention yet, but now I am. That is directionality. Notice the current source is pointing up. Well, of course, we could also have the current source pointing down instead, and that's the opposite way current. Well, surely the direction of the current source is important. The fact that the current's moving one way versus the other has some part to play in how these circuits are acting. And so certainly that should affect how I draw my voltage source. Because I could either draw the voltage source like this, or I could draw it like this, upside down, right? Where the voltage is going that way versus that way. And the way you figure out which way you draw it is exactly intuitive, exactly what you'd expect it to be, thankfully. It says, if the current source points up, then the voltage source points up. If the current source points down, then the voltage source points down. So here, the current source is pointing up, so my voltage source will look like that. And then that thing will be in series with the resistor. And I know that resistor is 5 because he doesn't change. There's my terminal, there's my terminal. And now what I have to do is figure out what should this number V source be so that it acts the same way as the original piece I'm trying to transform. And of course, that's Ohm's law. V equals IR. I, well, that's the 9. R, that's the 5. So this voltage source has a voltage of 45. Now I replace in my original circuit the stuff I circled in gray with the new transformed source. So it's the voltage source in series with the 5. Okay. Again, the voltage source is now 45. This resistor is still the 5. Now what's left? Well, I've got the 4 resistor. I've got the 3 resistor. I've got this voltage source here of 10. And everything else is there. So here's the 4, here's the 3, here's the 10. And of course, I'm looking for this I naught right there. Okay, so now what do? The rest of the problem is basic. No more tricks are necessary. Everything's straightforward. I've got everything in series, 2 voltage sources and 3 resistors. When we have 2 voltage sources in series with each other, we just add up their voltages. Of course, we worry about the direction. In fact, let me go ahead and just redraw it over here, just to give myself a little bit more room. Okay, 45, 5, 4, 3, 10, and I want I naught. Okay, so the next step, if I want to get this answer, well, the first thing I could do is just do a loop analysis, right? Just make a loop, do my KVL, Kirchhoff's law, calculate what must be the current. Or if I want to do it the more basic Ohm's law way, then I say, okay, here we have a voltage source, here we have a voltage source, they're in series with each other. The 45 is going this way, the 10 is going this way, so they oppose each other. So this is the same as a single source whose direction is given by, when you add these two together, is 45 plus negative 10, which is 35 positive. So 35, moving up. And then I have 5, 4, 3, and then there we go. 5, 4, 3. Now what do? Again, I'm looking for the current running here. I naught. So let me just add up the total resistance. So total resistance is 5 plus 4 plus 3, which is 9 plus 3 is 12. So now we have a single resistor, voltage source of 35, a single resistor of 12, and I'm looking for the current running through him. If I want the current, I is equal to V over R, so it's 35 over 12. Okay. Or again, I could have gone the loop analysis route. Say there's a loop here, I is right there. How do I get this? KVL says if I go around the loop once, and I add everything up together, I get 0. So I have plus 45 minus I times 5 minus I times 4 minus I times 3. And then I hit the 10 voltage source, but I hit big to small, so that's minus 10 is equal to 0. Okay. Now take all the i's on one side, so that's I times 5 plus 4 plus 3 equals 45 minus 10 is 35. So solve for I is 35 over 5 plus 4 plus 3 is just 12. And indeed, I get the same answer as I did before. Okay, so for this, it's very, very basic. There's not much to it. There's not that big of a trick. We've taken one of the sources with its associated resistor, and this is important. You can only convert a voltage source in series with a resistor or a current source in parallel with a resistor. You can't take a current source that's in series with a resistor and try to convert him. Okay? But here, You choose one of the sources. Again, in this particular example, there were two options. I could take the 9 amp current source in parallel with the 5, or I could have taken the 10 volts in series with the 3. I don't know which one to do. I try one of them. I tried the current source here. So I'm going to convert this current source in parallel with the 5 to a voltage source in series with the 5. I know the 5 is still there, so the only thing that's changing is instead of a 9 amp current, it's a something volt voltage source. What is that voltage? You just use Ohm's law, V equals IR. The current was 9, the resistor I'm talking about is a 5, 9 times 5 is 45. So now I've transformed this current source resistor combination into a voltage source resistor combination. And then I stuck it to the rest of my circuit. At that point, maybe there's more transformations to do, maybe there's not. In this case, we didn't have to do any more transformations, but certainly there are other examples where there's going to be a whole bunch of transformations you have to make. Then maybe you make one transformation that allows you to combine one set of resistors, but then you transform again. That'll let you do another set of resistors, and then you transform again one more time, and so on. Okay? But the basic premise is fairly straightforward. You have this type of source combination or that type of source combination. They're equivalent as long as you use Ohm's law to decide the numbers. The resistor in this case doesn't change though, at least the value of the resistor. You redraw your circuit after you've transformed, and then you look at what you have. What technique can I use to solve this? In this case, easiest way to do it was probably just the normal Ohm's law thing over here. However, if you like more fancy techniques, there's loop analysis that gives you the same thing. Okay? That's all there is to source transformation. Not too big of a topic for this one, but certainly there's a wide range of questions or problems you could work on to make sure you understand it. And I definitely suggest you do, because it's not always easy to see which transformation you should make first. Sometimes you have to make one transformation before you do something else. And the only way to know that is you practice a bunch of problems and you see how they work out. If you see you're getting harder and harder and more complicated, and you do a transformation and then you don't know what to do next, you're stuck, well then go back and try a different transformation. Try transforming one of the other sources instead. Anyway, that's all there is to source transformations. Let me know if you have any questions, and I will see you next time.